Hello, everyone. I'd like to thank the organizers of Café con Leche for the invitation to record this talk. I look forward to chatting with those that are able to join the Café con Leche Hour on May 9th, 2025. I am Selenne Bañuelos, Associate Professor at California State University Channel Islands, and I'm also currently serving as the Associate Director IPAM, the Institute for Pure and Applied Mathematics, which is currently one of 6 NSF-funded math research institutes in the country, and it's located in UCLA. I chose to record this talk on work that was done a couple of years ago now, because, well, this topic is quite relevant to all of us. We all sleep. There are parts that are definitely accessible, while the mathematical analysis of the model is pretty great. So. And also I have yet to actually record this talk. So I figured this was a great topic. I'm not going to take time at the beginning of this talk or the end to share a story about my career trajectory, as I'm fortunate to have a chapter in the Testimonios book. So I invite everyone, if they'd like to know a bit more about me, to read the chapter and the testimonials. And I will take some time though at the end to share a little bit more about what's going on in IPAM and what kind of programs we have planned, and hoping, just to let y'all know, what's happening there, and hopefully y'all can apply or propose other programs as well. Okay, so let's get started. A little bit about myself. My research interests is that I create, analyze, and simulate mathematical models with applications to biology. The models or applications that I generally work on are only time dependent, and so the models are created with ODEs, or difference equations. The sort of tools that I use are bifurcation analysis, sensitivity analysis, parameter fitting, and so on. I have projects in population dynamics, epidemiology, but I'm mostly interested in physiological systems like sleep, for example. And I'm also part of this great group now that's modeling phage treatment for bacterial infections that are resistant to antibiotics. So let me introduce you to the team that did the work on sleep and the 2 papers that came out of this. I'll link those at the end. From left to right, we have Dr. Pamela Pisa, who was at Kenyon College of Ohio at the time. Dr. Alicia Prieto Langarica, who is a professor at Youngstown State University in Ohio as well. Dr. Janet Best, who was the research lead for this project. She's at The Ohio State. Dr. Shelby Wilson, who is at the Applied Physics Lab at Johns Hopkins. Dr. Gemma Huguet, who was also another project lead for this research. She's at Universitat Politécnica Catalunya in Barcelona. And we're also, in this collaboration, we work with Dr. Marcus Schmidt from the Ohio Sleep Medicine Institute. Great, so let's begin with the outline of this talk. I'm gonna first introduce, what we know about human sleep patterns. And then we're gonna build the model by looking at the sleep-wake portion of the model. And then once we're actually asleep, the cycling between REM and non-REM. So again, all this will make sense once we go through the first things about human sleep patterns. And then we're going to talk about incorporating thermoregulation in the model, like why we care about it, what is it useful for, and how we do so, and some simulation results. And again, as I mentioned, I'm also going to take a minute or two at the end to just go over the IPAM webpage. Great. So the objective here is to try and answer the question, what role might temperature have in shaping the structure of sleep? Great. So let's start with the human sleep patterns. We know a couple of things about the characteristics of sleep. It is a loss of consciousness. We have decreased muscle tone, increased sensory thresholds, and it is non-uniform. right? We alternate between various stages, and these are rapid eye movement sleep or REM sleep. It's usually when we associate it with dreaming, or non-rapid eye movement sleep or non-REM sleep. Um, Evolutionary speaking, there are disadvantages of sleeping. It's a time in which we're vulnerable to predators, a time not spent on resource acquisition, time not spent on reproduction, and a time not spent caring for offspring, right? So there are, again, evolutionary speaking, disadvantages to sleeping. And yet there are consequences if we don't, there's sleep deprivation. We see that in animals, there's a severe pathology, skin lesions, increased food intake, weight loss, and even death. So we all do it, we all sleep, and yet we don't know why. There's no overall consensus of like why it is that what is the ultimate function of sleep. Okay, so let's talk about some brainwave patterns, because we're going to, again, how are we going to model what we're talking about when we mean sleep? So here we have electrical activity of the brain. These are done by an electroencephalogram or an EEG, which tracks brainwave patterns. Sleep researchers usually break down the non-REM time of sleep between 3 or 4 different stages. For our purposes, we're not going to differentiate between the different non-REM stages. We're going to just say this is non-REM. During non-REM, though, actually, I think there's a laser pointer. During non-REM, we have decreased level of metabolic activity in the brain. This is characterized with high amplitude, low frequency EEG activity, and is often considered the most restful state. This is what we call slow wave sleep. Note that during REM and wake, we have high brain metabolic activity characterized by low voltage and fast EEG activity. So what's the difference between wake and REM if our brain wave patterns look similar? It's the absence of skeletal muscle tone. So while we are awake, we have fast EEG activity and we can move. While we're asleep in REM, we have fast EEG activity and we don't move. And then while we're asleep in non-REM, we have slow EEG activity and we can move. So this is a time at night where, you were asleep on one side of the bed and you found yourself on the other side of the bed in the morning. It's because you were moving during non-REM part of sleep. Okay, so let's talk about a sleep hypnogram. This is what we normally see in a typical human sleep pattern. This is a typical night of sleep in a circadian entrained human adult. So a couple things that we know to look out for is that sleep begins in non-REM. So again, instead of when I show you our simulations, we're not going to be looking at these different stages of non-REM. It's just going to be clumped up into one non-REM bout. So here's the non-REM bout here. When sleep begins, we're in non-REM, and sleep ends in REM sleep. We have 4 to 5 cycles per night. So the cycle of non-REM, REM, non-REM, REM. The average period of a given cycle, so average period of one of these cycles, is approximately 90 to 100 minutes. For a given cycle, we know that the REM bouts are shorter than the non-REM bouts. And we also are taught to expect that the REM bouts get lengthened throughout the night. So at the beginning part of our model, we wanted to simulate this. We want to have these typical human sleep patterns on our model, and then incorporate temperature into it. So we're going to see how we actually got pretty darn close to simulating these sleep patterns. So let's first start with talking about the neuroanatomy of sleep. There are some key areas that are active during the waking state. These are the midbrain reticular formation, or MRF, that helps maintain wakefulness by inhibiting sleep active neurons. And the orexinergic neurons of the hypothalamus, they also help stabilize wakefulness. So these neurons then are active during wake. We know that damage to the orexinergic neurons can produce narcolepsy and hypersomnolence. Neurons in the preoptic area of the hypothalamus, or POAH, and in the population located near the tail in the brainstem reticular formation, or CRF, are sleep active, and they have mutually inhibitory connections with the MRF neurons. So you'll see all of this in a diagram in a minute. But another part that is important and will come up later in the talk is that the POAH has temperature sensitive neurons. So at first, we're building this model. Of course, there are different models out there that we could have built off of, but we concentrated on those existing models that already have a POAH area of the brain because we wanted to incorporate temperature, and that was a perfect place to do so. We also know once we're actually asleep, we know that neurons that inhibit REM sleep, so to stay in non-REM, these can be found in several nuclei, including the locus coeruleus. These are several areas of the brain, but when it comes to our model, we're just clumping them up in one population and calling those the REM off or non-REM parts of the brain. So here's so let's talk about the model, the sleep-wake model and REM non-REM. So at first, we're going to build the model to discuss how we transition between sleep and wake. And then once we're asleep, we're going to talk about the sub-circuit of REM and non-REM and how we oscillate between these cycles. Okay, so here's the diagram. This is the model diagram depicting the interactions between the neural populations. These are the ovals, and the processes, which are the rounded rectangles. The interactions between the populations are denoted by lines, and they can be excitatory if they end in an arrow, or inhibitory if they end in oval. And as I mentioned before, we know that there are mutually inhibitory connections between the POH-CRF and the MRF. So we know to expect this, and again, this is in the model. Okay, so let's talk about the sleep-wake portion of the model. We're first going to talk about the dynamics that led the model to transition between sleep and wake. So that's really characterized by this top portion of the diagram here. And there are two forms of modulation of the sleep-wake system in our model at thermal neutrality. So again, assuming no temperature here. This is the circadian process and the sleep homeostatic process. So what do we know here? The circadian process, the suprachiasmatic nucleus of the hypothalamus, acts as an endogenous oscillator that generates the circadian rhythm. It can be entrained to like a 24-hour light dark cycle by inputs from the retina. It provides input to the POAH and RX populations, as we see here. And we model this input as a circadian pacemaker, C of T. The figure here displays the course of the associated circadian current. But really what I want you to see here is that what do we know about our circadian process is that as we progress during the day, or getting close to the night, this is when we're in the falling phase of our circadian current. And as in the morning, once we wake up, we're in the rising phase. So again, this is going to be relevant because as we are getting closer to the night, the connection, right, the current coming from the circadian process is diminishing. It's in the falling phase. And so we're not putting so much inhibition into the POAH, which means that at some point we lose the power from the circadian process going into the POAH, which allows this one to activate, and then we're asleep. So again, we're going to talk about how all of this comes together in the model, but that's just a good visual to keep in mind as we move on. Now, the homeostatic drive for sleep, this is our propensity to sleep over time, right? We know that this increases while we're awake, and it decreases during sleep. So the model for this is actually quite simple. We have the homeostat variable H is modeled by the differential equation H prime. Script H here is a Heaviside function, a step function, which means that it's script H gives us the value 1 when the input is positive. It gives us the value 0 when the input is negative. So we note here that the homeostat variable is dependent on the activity of MRF. So for example, during wake, right, we want this to increase. During wake, the MRF is active and above some threshold. And so this difference here is positive, which means that this Heaviside function is 1. This one is 0. So we have H prime equal to 1 minus H over tau 1. Therefore, H is increasing, right? When we are asleep, MRF is inactive. And so we have this part here now is positive, which means, and this is 0, which gives us H prime equal to negative H over tau 2 decreasing. Right? Okay, so again, recall that this homeostat variable, this modeled by this differential equation, is feeding into POAH here only. Okay. So let's talk about now the neuronal components of the model. So the mean activity level of each neuron population is modeled using the Morse-Lacar equations. You might recall from a course in human physiology when studying the activation of neurons that there's a complex relationship between the membrane potential and the activation of ion channels within the membrane. These equations describe that complex relationship. The potential depends on the activity of the ion channels, and the activity of the ion channels depends on the voltage. So in other words, it helps us simulate when the neurons are activated or firing and when they're inactive. These equations this is a 2D system. These equations are named for Kathy Morris and Harold Lacar, who derived them in 1981. It is one of the favorite mathematical models, I did say, in the area of computational neuroscience. It was originally developed to describe the excitable behavior of a single neuron, but here in our model, we're interpreting the model variable V as which is the membrane potential, as the mean activity level of the entire population for each of these populations. So each of these populations has its own set of Morse-Lacar equations. So yeah, like with I equal to each of these, right? Okay, so I'm not going to spend too much time on this screen, but just to show you that, again, there's quite a bit going on in the model, right? So every population, it is described, the mean activity is described by this set of 2D equations. And yet, of course, there are synaptic currents from one population to another. So that's ISIN, and they're given here. So again, these connections here are like, as you saw them in the diagram before, all of these connections. Okay. But we will actually take a minute here to provide a description of the sleep-wake cycle based on the evolution of the nullclines. So if you've taken a course in differential equations or dynamical systems, you know that like the nullclines, you can find what these are when you set the differential equation equals 0. We're going to be talking about the VPOH, WPOH, and VMRF, WMRF phase planes, because again, we know that when POH is active, this is when we're asleep. When MRF is active, this is when we're awake, and these things have mutually inhibitory connections. So for a frozen synaptic input, the V nullcline is cubic shaped. So again, when setting this equal to 0, for frozen synaptic input, this is cubic shaped, and the W nullcline is sigmoidal. Okay, so the dynamics on the phase plane, it's important to note that these are also of the slow fast type. So the dynamics of V is faster than those of W. Each neuronal population receives input from other populations. So as the amount of input received changes over time, the V nuclein changes its position on the phase plane and crosses the W nuclein at different points. So the V nuclein is going to be shifting up and down and then crossing the W nuclein at different points. And this is when we know that we get our steady states, our fixed points, right? So one important thing to note is that the W nuclein stays put because it has no input from the synaptic currents. So it's only the V nuclein is moving up and down. When the V nucleins are high, so when the V nucleins are up here, indicating strong excitatory or low inhibitory drive, they cross the W nuclein on the right branch, defining a stable fixed point of high activity. In other words, on. And by the way, for those who are studying dynamical systems, I do want to note that this is only like a real fixed. This is a real fixed point only when the synaptic input is frozen, right? Otherwise, it's a fixed point. When the V nucleins sit low, indicating strong inhibitory or at the same time low excitatory drive, they cross the W nuclein on the left branch, defining a stable fixed point of low activity, in other words, off. Finally, when the V nuclein crosses the W nuclein in the middle branch, they define an unstable fixed point and a stable limit cycle of periodic activity naturally occurs. Okay, so let's talk about these different sections here, so we can see how we're getting, between sleep and wake of the model. So first, I do want to remind you again, we've seen this before, but the POH and CRF are active during sleep and the MRF, ORX are active during wake. And then at the same time, these are off during those different stages. Okay, so in these graphs that you see down here, the first one, we have the time course of VPOAH, again, the membrane potential of POAH over 30 hours. So this is over 30 hours is the membrane potential. And then on these graphs over here, we have this trajectory, the projection of the trajectory on the VPOH, WPOH phase plane and the VMRF, WMRF phase plane. So again, we have this trajectory here projected onto this plane. So we have this black curve that goes here, and then we have this black curve here. It's the same trajectory, but projected onto these different planes. And again, I have to mention that the dynamics of the phase plane is also the slow fast type. The dynamics of V is faster than those of W. Then also I'll notice that here, this gray curve you see here is the W nuclein of POAH. Again, it does not move. And we see the same gray curve here of the VMRF, WMRF phase. So the WMRF, the W nuclein of MRF. Okay, so let's talk about what all these different dots and colors mean. So at the beginning of the wake state, so this is the red dot here, the VPOH sits at its lowest position, which is associated with this red nuclein. Here, the excitatory input from the homeostatic process is at its minimum value, and also the inhibitory input from the circadian rhythm is starting to rise, right? We're at the wake state, at the beginning of the wake state. So the system sits on this stable fixed point that lies on the left branch of the VPOH nuclein, this is when POH is off, right? The silent state. At this moment, the MRF, which is this red curve here, the MRF is not receiving inhibition from POH because POH is off, and the VMRF, WMRF nucleins intersect at the right branch, which is the active state for MRF. Now, during the wake state, the homeostatic drive is starting to rise, right? While we're awake, it's starting to rise, and the circadian current is in the falling phase. So the inhibitory connection to the POH is starting to weaken, and the VPOH nuclein starts to move upward. So we go from this red one to this green one here. So the trajectory is tracking that stable fixed point on the left branch of the VPOH until transitions to the middle branch and destabilizes. Remember, this is an unstable fixed point. At this point, the trajectory jumps to the right branch, pushed by the fast dynamics of V, fire rate, indicating the onset of the sleep period. So this now, we're on the right branch now in the blue. So here's where we like intersect the V and W null climb, which is when, again, the POH is now active, and so now we're asleep. Then during the sleep period, so now we're asleep, the homeostatic drive is reducing, and the circadian rhythm is rising, causing a downward shift of the null climb. So now we're moving back down. So we're going from the blue null climb, transitions to the orange one, and the trajectory follows that stable fixed point. But the sleep period ends when the VPOH null climb shifts sufficiently low so that the stable fixed point moves to the middle branch, destabilizes again, and the fast dynamics pushes the trajectory back down to the left branch. So that's how we get our model to just transition between sleep and wake. So again, here we have the membrane potential of POH being active. And now here we have the membrane potential of MRF being active. And of course, the parameters had to be changed in a way that made sure that we had POH active for 8 hours, which is what we're hoping for. Great. So now let's talk about the REM, non-REM subcircuit. So now we're assuming that we're asleep, and we want to get a couple of things, right? We want to make sure that when we fall asleep into non-REM. We want to make sure that when we're waking up, we wake up from REM. We want 4 to 5 cycles between non-REM and REM. The REM bouts need to be shorter, right? There's quite a lot of things that we need to happen. And so the dynamics of this part here are very important. I will say that I'm actually jumping ahead a little bit here because I'm going to talk about temperature. And that's because in our second paper, so I'm actually, as I mentioned before, I'm cheating here a little bit because I'm sort of mixing 2 papers in one during this talk. But in our second paper, we made some changes to the inhibitory connection from the from the POH to the REM off, so that it was actually temperature dependent. This was to achieve some other things that we did not see in the first paper, like for example, the duration of REM bouts. We need to make sure that these were actually being disturbed because of temperature, and also that there was an issue with how quickly we got our first REM bout, given the temperature effects. So that's something that we did in our second paper. So the synaptic current, as I mentioned, from the POH to REM off neurons includes this additional multiplicative term SYN. So if you read our first paper, there's actually much simpler equation here. When SYN reaches a certain critical value, which is about 0.327, again, these are values from our first paper, the POH inhibits REM off neurons strongly enough so that oscillations between REM on and REM off neurons emerge. So we'll see the bifurcation curve for this in a minute. The variable M, by the way, measures the amount of metabolic processes that the body needs to activate in order to keep the body temperature at its target value. We're going to see this again when actually like incorporating ambient temperature into the system. So you'll see that part again in a few minutes. Okay, so here, during the sleep stage, the ORX and MRF neuronal groups are suppressed and the POH is active. In order to analyze the regulation of REM cycling, we are going to isolate this subcircuit by doing a couple of things. Well, first of all, we know that the MRF and ORX are inactive, so we can just ignore these connections, right? So we're going to ignore this connection, ignore this one, and ignore this one. And then we're going to consider the strength of the inhibitory input from the POH, SYN, as a parameter. So again, now we're going back to the stuff that we were doing in our first paper. And remember, SYN was a term in the synaptic current of POH REM off. So again, but for different reasons this time, again, for those dynamical systems people, the W null climb won't be moving. That's the important part you need to know here. It's the VR off null cline that will be moving up and down, or the V null clines that will be moving up and down. But before we get there, talking about like the null clines, let's talk about this bifurcation diagram of the REM subsystem. So for small values of sin, so for values of sin between say 0 to, I think it's 0.327, something like this, the system has a stable equilibrium point with high VR off. So this is when we're in non-REM, which loses stability through a hot bifurcation at about 0.327, where a stable limit cycle is born. The stable limit cycle persists over a range of sin values. And the second figure here shows the period of the oscillations within this range of sin values. And we see a lengthening of the periods during the night. So that's going to be important. The stable limit cycle disappears then via another half bifurcation when sin is 0.668, where the system then has a stable equilibrium point with low VR off, in other words, in REM. So again, this is what we were hoping to achieve, so that when we fall asleep, we have a stable on non-REM, right? So non-REM, we start with non-REM, and then towards the end of the night, for later values of sin between 0.668 and 1, now we're in REM, right? Okay, so this next, it's just an example. It's not as interesting as the next one here. Here, the idea is we actually have this. I wanted to show you those two values. So we're talking about what's going on in this regime here. So when sin is 0.3, and then when sin is 0.7, just to see what this looks like. So these are the null clines. Again, the W null clines don't move. It's the V null clines that are moving. And here we have the null clines for different values. So this is the V null cline when sin is 0.3. And this is the V null cline of R on when sin is 0.3 as well. So for small values of sin, like during sleep onset, the REM off neurons are active, right? And the VR off null cline intersects the WR off null cline on the right branch. And the opposite is happening with the R on null clines, neurons, right? So they're mutually inhibitory, and that works out fine. For large values of sin, like when we're about to wake up, the VRF null cline, so this is, for example, 0.7, this is past that point, the VRF null cline shifts down and intersects the W null cline on the left branch, so inactive. So the REM off neurons are inactive, and then the REM on neurons are active. Again, that's just how we make sure that we fall asleep into non-REM and wake up in REM. But now let's talk about that middle portion, right? So the middle portion is important because this is where, again, we want to talk about these 4 to 5 cycles. We want the REM bouts to be shorter than the non-REM bouts, but we want the REM bouts to be elongating. So here's, again, just an example to sort of paint this picture. In these graphs, we have a singular value sin. This is 0.6. Okay, so here sin is fixed to 0.6. And this is the projection of the stable limit cycle for this value of sin. This is the black curves here, together with the V null clines. These are the blue null clines here, and the W null clines are red. So in this graph here, we have the projection. So we have REM off onto VR off, WR off phase space. And here we have REM on onto the VR on, WR on phase space. But the important thing to note here is that this is a 4D system, so a 4-dimensional system. The V null clines in a given phase plane are moving up and down as we trace the trajectory in the other phase plane. So for example, the VRF null cline depends on the current value of VR on. The second graph shows the projection of the limit cycle on VR on, WR on phase plane, where the REM on population is transitioning between these two fixed points. As VRF is ranging between its minimum and maximum values here. We have made a parameter in the system a function of VR off so that in this state, the REM off trajectory travels up along the active phase or the right branch of the VRF null climb slower than it travels down the silent phase. So as we are in non-REM, as you saw in that previous the diagram with the increasing periods, while in this oscillatory regime, we see a lengthening of these periods during the night. So moreover, since the position of the VRF null climb moves downward on the VRF phase as thin increases, it has the effect of lengthening that portion of the silent branch of the VRF null climb that the trajectory is tracking while shortening the active part of the branch, which is how we're able to model an increase in the length of the REM bouts as sleep progresses. So again, this is the whole null climb conversation about how we got the model, the bifurcation analysis and all that to make sure that the model was working the way it was. And all of this description is on the first paper. And we did, in fact, achieve what we were hoping for. So again, you've seen this part of the graph here before, which is when POH is active and MRF is active. So this is sleep time, this is wake time. So now during sleep, we're going to be looking at this portion down here. So the blue curves that you see up here, again, when they're positive, right? This is when REM off is active. In other words, non-REM. The red curves that you see here, this is when REM on is active. In other words, when we're in REM. So we did achieve a couple of things that we wanted. And by the way, so the graph that you see here, this is actually from our second paper because we were able to improve how we saw this in our first paper. But we do achieve a couple of things that we wanted, right? Approximately 8 hours of sleep period followed by 16 hours of wake. We have five non-REM REM cycles per night. The REM bouts are lengthening across the night. So as you can see, here is the REM bout, the first REM bout, quite short. Now we have this longer one towards the end of the night. The REM bouts, those still make up a smaller portion than the non-REM bouts in any cycle, right? And yeah, we fall asleep into non-REM and wake up from REM. So those are the things that we wanted. And there are actually a number of more subtle experimental observations that are pretty well replicated in the model as well. So we know that REM should constitute approximately 20% of sleep, and our simulations actually yielded REM to be 20.3% of the night. The first REM bout, again, without any temperature effects or anything like that, should be about 5 to 10 minutes long and occur approximately 100 minutes into the night. So that's when you should get the first REM bout when you're asleep. And our simulations exhibit that the first REM bout was 8 minutes long. And again, it should be between 5 and 10. So we got 8 minutes and it occurred 101 minutes into the night. So again, pretty great. We were able to simulate the sort of characteristics we expect to see in sleep. Okay, so now let's talk about thermoregulation, right? So what started it all, why we were even interested in looking at this project. And I'm sorry, I'm saying I'm actually running out of time here, so I'm gonna go a little faster. But this part is easier. So what is thermoregulation? It's the process that allows our body to maintain its core internal temperature. And our core internal temperature is 37 degrees Celsius. Thermoregulation mechanisms are designed to return the body to homeostasis again. So what do we do to return our body to homeostasis? So how do we do this? There are intercorporeal transport of heat, by blood circulation. So, vasodilation, vasoconstriction. So our blood vessels will constrict when it's really cold, so that there's friction. We shiver right when we're cold. We sweat when it's hot. And we change body positions, right? So we might shrivel up, we get closer to our bodies when it's cold, and when it's hot, trying to spread away. So again, these are the kinds of things that we can do to thermoregulate. But the important thing to note, as we mentioned some of this before, we don't move during REM. In fact, we also don't thermoregulate, some, but definitely not as well during sleep when we're in REM. And non-REM you do. So you're actually sweating during non-REM. You can move around during non-REM. If you're really cold, you can actually move into those positions. But while you're in your REM, you cannot. And so again, going back to the sleep hypnogram, So again, why is thermoregulation important? Because during this entire section of our sleep, when we're in REM, we're losing the ability to thermoregulate. And so if the room is really, really cold, and we're asleep and we can't move and we're not shivering, we're not vasoconstricting our blood vessels, all of this stuff, then our body temperature is not going to maintain its core temperature. And so if we don't wake up, we will die. And so it disrupts our sleep, right? So the motivation is that thermoregulation may have a key role in shaping human sleep patterns. And understanding thermoregulation remains an important challenge in sleep research. But also in terms of the model, it's actually pretty great to incorporate it because it's an external input, right? It's an external temperature input. So it lends itself as a natural input to a sleep model. And then also in terms of sleep models, again, ours model is not the only one out there. But the challenge would maybe pose to others is to, if you have a sleep model that's working, that has, again, all of these characteristics of sleep that we know, and then you incorporate the sleep model, as this external input, it'd be interesting to see how well or not so well the model behaves, right? So these are all like motivations for incorporating temperature regulation, or thermoregulation. So again, how did we do this? So again, as I mentioned in the first paper, the temperature effects would really just be this external input into the POH, and then later on in the second paper, we also added it in the SYN variable in our connection between POH and REMA for the subcircuit. But following the work of Nijet et al., we modeled the thermoregulation as this differential equation here. So let's talk about it. Again, you've seen at least this portion here as M earlier. So let's talk about the equation a bit more. T set is the temperature the body is trying to maintain, right? It's our target body temperature. TB is the core body temperature, and TA, is the ambient temperature. And again, recall that T set, the target body temperature, is 37 degrees Celsius. Although T set does, in fact, fluctuate a half degree Celsius around 37 degrees Celsius. According to the circadian rhythm, and we do know this, our body temperature actually lowers a bit as we're getting towards the night, as we're getting towards sleep. Okay, so the first term of this differential equation, TB, is the rate at which the body heats or cools as a function of the difference between the ambient temperature, TA, and the body temperature, TB. The second term, Tm, is the rate of endogenous metabolic heat production. And the third and fourth terms of this equation model the processes of active thermoregulation. So for example, the third term describes the rate modeled by Michaelis-Menten equation, at which the system raises the body temperature when it deviates from T set. We do have different different constants here, like VC, KC. These are different constants because we do know that our metabolism works differently for cooling than heating. So those are different variables in the model. Okay, so let's talk about the steady states of this differential equation. The black curve here shows the steady states of the full equation, so this entire thing. And again, this is when T set is 37 degrees. And there's the black curve, the steady states of the full equation as a function of the ambient temperature TA. So we're varying the ambient temperature, again, temperature of the room, between 0 degrees Celsius and 50 degrees Celsius. We tuned the parameters controlling the metabolic processes responsible for thermoregulation so that we can mimic what we know is biologically plausible ranges of environmental temperatures over which our body can maintain its core temperature. And this is between like 10 degrees and 37 degrees Celsius. And in other words, again, our body will be able to do what it needs to do in this range of temperature in the room so that we can maintain our core body temperature. If it gets too cold, we'll need clothes, we'll need, blankets and so on. We'll need to actually like move around and jump around or something like this. If it gets too hot, maybe we need an air conditioner or need ice and so on. Again, to maintain our core body temperature. So this is the range in which our body will take care of itself. Now, the blue curve that you see here, this is while we're in REM. So again, when we're in REM, we know that we're not thermoregulating. And so these parts of the equation here are zero. So we have the steady states, we're really looking at the steady states of the function, TB prime equal to K, this again, the first term and the second term. But again, the steady states are when we set TB prime equal to zero. And so we just get TB to be a function of a linear function of TA, which is why we get this curve here. But the important thing to note here is that, again, if we are in REM and we are in an ambient temperature of, say, 27 degrees Celsius, then our body temperature will stay there and everything will be fine. If we deviate from that, then our body temperature will, like, if it gets hotter, right? If it gets hotter in the room, then our body temperature will tend towards that as well. Okay, so let's now talk about how this works into the model. First, by looking at just a graph of what happens. So here, whenever the body temperature TB deviates, so TB is this blue curve here, and Tmax is this greenish blue curve up top. Whenever a TB deviates more than 0.2 degrees Celsius from thermoneutral, again, TB should be like following this here, the system triggers an inhibitory pulse to POAH. So it inhibits POAH. Again, POAH is on while we're asleep, right? But during this time, it inhibits POAH, so it kicks it on. So what I want you to look at here is, again, we're asleep, right? POAH is active during this time, right? But when we are in a REM bout, when we're in REM here, this is the time at which our body temperature will increase because the room is really hot and we're not thermoregulating. And so we set this bar of 0.2 degrees. Like once you hit 0.2 degrees more than where TB should be, there is this like kick to wake up. And so then POH falls and so on. So this is how we made sure that that we were, again, like waking up the system, as we all need to wake up when the ambient temperature is different. So I'm not going to actually take too much time in this next part, but I did want to actually just point, because we've talked about null clients enough. But if you want to take a look at the first paper and read through this, you'll see, again, we discuss the dynamical effects of the inhibitory current on the dynamics of POH based on, again, the null client approach. So you can take a look at that as well. And I'm running out of time. So, okay, so let's talk about some simulation results. Here, this figure shows, first I want to mention that that we were actually, as we're simulating all this, we of course wanted to compare it to some experimental results. There are, so the experiment that we were actually looking at a bit more closely was conducted in the 1980s. They had 6 male subjects between the ages of 18 and early 30s, where they had them sleep in boxers only, so no blankets or anything like this, and the ambient temperature was controlled the entire time. So when they walked into the room, there was a given ambient temperature. They didn't change the temperature during the night. They left it as it was, and there was controlled humidity and so on. And according to these experimental results, ambient temperature of 29 degrees Celsius, which is about 84 some degrees Fahrenheit, is supposed to be the perfect temperature at which to sleep. And again, I know it sounds like a lot, but we're talking about no blankets and so on. And again, though, I'm very curious to know like what the results would have been had they done this experiment with women, for example, but it was just 6 male subjects. Yeah, so they had the subjects sleep for several, it was for several nights, but again, a given temperature every night at 29 degrees, 34, 37, and then colder at 21 degrees. So in our model, again, the POH is active the entire time during sleep. There's no awakenings that occur during the night. But as we deviate from this ambient temperature, is supposed to be, again, 29 degrees is supposed to be the perfect ambient temperature. As we move away from it, due to the increased need for thermoregulation, right, due to need to wake up, the number of awakenings per night increases as the ambient temperature deviates from thermoneutral. And again, it gets worse as we move away from that. So let's compare this to some of the experimental results. What do we know? So this is from the Haskell et al. Paper. And again, notice that they have the different stages of non-REM. We just call them non-REM. And they're talking about the total sleep time, sleep latency. Sleep latency is how long does it take to fall asleep? So let's look at what we found here. That away from ambient temperature, away from ambient temperature of 29 degrees Celsius, there's no significant effect in the time to fall asleep. And again, our model found that as well. But they did find increased amount of wakefulness and a decreased amount of REM sleep. So the amount of REM sleep was also being affected. And in our model, we also found, again, like in comparison to our model simulations, that there is a significant reduction in REM sleep at 37 degrees, that there is in fact a quadratic relationship between the amount of REM as a function of the distance from thermoneutrality. So we're able to see those things as well. And in fact, with our second paper, again, we were also able to talk about this REM latency. So how was the time at which we had the first REM bout affected because of the ambient temperature? And then how does that, how it hurt the number of REM cycles we had in total? Okay, so let's summarize now what we've talked about. We have a sleep-wake model that's incorporating ambient temperature as model input and body temperature as a model component. The system produces awakenings from REM sleep to thermoregulate via temperature-dependent REM homeostat. So that's, again, part of the second paper, and an awakening drive to the POH. Trends in sleep behavior are consistent with some experimental work, although we made this pitch from our papers that it would be great to have these kinds of studies done again and data shared. The changes in sleep characteristics are due to variations in sleep quality from sleep history. So this is actually what we were looking at in our second paper. We were looking at what happens if we have the model or the subject, right, the person, sleep in the same bad temperature a number of nights, and how does that affect? So what is the long-term effect of sleeping in these different ambient temperatures, and how that affects the whole thing? So I invite you all to read these papers. Great. So then I will share them here. These are those two articles. So the first article was, again, like the derivation of the model, and the second article was kind of clean, just trying a few more things in the model and then looking at the long-term effects. And I'd also like to acknowledge that all of this work was done by support from the IMA, the Institute for Mathematics and Applications, which at the time that we met there as part of the workshop for women in applied math was an NSF-funded institute, as was MBI when we were there. And again, we'll like to thank the National Science Foundation for their support as we were working on all this. And I would like to end this slideshow here for a minute and talk about IPAM. As I mentioned, is an NSF-funded institute at UCLA. It's been almost 25 years old. So here's the webpage. If you go to the long programs, you'll be able to see that we have programs planned up until spring of 2027. So the long programs are 3-month-long programs. We invite researchers from all over the world to come to IPAM and work on a specific research area, but usually we have people from different sub-disciplines, all with their own sort of angle of looking at a given problem. So for example, right now at IPAM, we have a program on non-commutative optimal transport in the in the spring, excuse me, in the fall of this upcoming year, 2025, there is, this transitioning from deterministic to stochastic interactions modeling in electrochemistry. In spring of 2026, we'll have a long program on multi-fidelity methods for fusion energy. In fall of 2026, I know I've already talked to a couple of people in the Lathisms community who are interested in this quantum topology program. And then again, spring of 2027, numerical algebraic geometry and correlation electronics. So please take a look at these long programs. You can apply to be at IPAM for the entire long program. And within the long program, it has workshops. So really more like mini conferences. And during off workshop weeks, this is when you're really actually getting to do work and collaborate with a whole bunch of people, which is really great. So if you go to the workshops part of the program, you'll see here, so this is, for example, part of the long program on non-commutative optimal transport, right? So it tells you here, if a given workshop, if it has a number in front of it, it's part of a long program. But also if you come down to this part, these are standalone week-long programs that we hold in the winter. So these are January and February of 2026. And then there's one more on this side of the page, Math of Cancer open problems in February. So I invite you all to take a look. Again, these programs are really for, more senior graduate students, postdocs, and so on. We do have some programs for undergrad students, but, just take a look at the webpage to see what we have going on. And I also encourage you very much to look at the web pages of other NSF-funded institutes. So, for example, we have so there is MC in Chicago, ICERM at Brown, AIM at Caltech, SL Math at Berkeley, and I hope I'm not leaving. Oh, IAS, of course, Institute for Advanced Studies at Princeton. So please do take a look. And yeah, I hope you all take advantage of these research communities built by these NSF-funded research institutes. A lot of amazing work is being done here. So thank you all for your time, and I look forward to seeing you all in a bit.